All right, here we're looking at a question about the relationship between a weak base and its weak acid, the chemical structure, like the molecular identity of it, as well as how can we take a Kb and calculate a Ka. All right, so we're looking at pyridine here. You don't need to draw out the structure, but you could if you wanted to. Okay, those carbons, these are carbons, and then each carbon has an H on it. Okay, and so I think it's just helpful to visualize this. You don't have to do this on the exam, but that nitrogen has a lone pair on it. That's why pyridine can act as a weak base. It's got this lone pair on a neutral nitrogen compound, which is likely to, every so often, grab a proton from water, which means that we are going to form the conjugate acid, which looks like this. Okay, and this whole thing is charged. Okay, it's a plus charge, all right? And then we would also have been generating some OH minus, which again means that this was functioning as a weak base. All right, so chemically, what did we do? We gave pyridine a hydrogen and we put a positive charge on it, right? So we're looking for an answer that is this plus an H plus, all right? I accidentally already marked the answer on here, so we're looking for that right down there. But anything else here that didn't have that, we could have excluded. So there's only two answers here that have the right conjugate acid listed. You don't even have to do the calculation for Ka. Between these two options here, only this one makes sense. Remember that Kas are always very small numbers. If it was this giant times 10 to the 8th, then that would mean it was an incredibly strong acid. We know that that's not true. It's weak. But the way you get that is you remember that the Ka of an acid times, well, let's do it the other way. I'll see it the other way because we started with a Kb. At the Kb of a base times the Ka of its conjugate acid equals Kw, which is 10 to the minus 14th. Again, I didn't specify room temperature, but that is always assumed unless stated otherwise. So Ka of our conjugate acid will be 10 to the minus 14th divided by 1.5 times 10 to the negative 9th. That gave us the 6.67 times 10 to the negative 6th. Okay, so this is a really important relationship, and especially to remember that it's not just for any random base and any random conjugate acid, like it has to be the connected pair, right? Like mathematically that only works when you're using Ka and Kb of the conjugate acid base pair. So don't try and apply that to anything else. It has to specifically be for that pair.